Okay, welcome back to the second talk of today from Professor Emilia Bazhlekova, who is a full professor, Doctor of Sciences at the Institute of Mathematics and Informatics, Bulgarian Academy of Sciences. She received her PhD degree in 2001 from Eindhoven University of Technology in the Netherlands. Her PhD thesis, Fractional Evolution Equations in Banach Spaces, has been cited more than 900 times. The main field of research of Emilia Bazhlekova is fractional calculus and its applications, analysis of generalized fractional evolution equations, subordination principle, operational calculus approach, applications of fractional calculus in linear viscoelasticity, with research results published in about 50 papers in international peer-reviewed scientific journals with more than 1,000 citations. She is an associate editor of the international journal Fractional Calculus and Applied Analysis. And today she is going to speak to us about multinomial Mittag-Leffler type functions, basic properties, and some applications. Please go ahead. The floor is yours.
Thank you. Thank you for the kind introduction. And also I would like to thank the organizers and all participants for this useful seminar series. The subject of my talk will be multinomial Mittag-Leffler type functions, some of their basic properties and some applications. Let me first give the definition. The definition is given in equation 1. This is a function for where delta is the Pohammer symbol. When delta is 1, this function is introduced in a series of papers of Luchko more than 25 years ago in the context of multi-term equations, equations that contain multiple fractional derivatives. In the original papers, this function with delta 1 is named multivariate Mittag-Leffler function. Later, for delta arbitrary real number, it is introduced simultaneously in paper 3 by Arran, Fernandez and co-authors, and in our paper 4. Our motivation to define this function was the following. In our study of non-local problem for multi-term type fractional diffusion equation with non-local boundary conditions, except of the functions defined by Luchko, it was necessary to extend the set of these functions such that it contains also the convolutions of such functions. That's why the motivation, this was the motivation to introduce the functions in equation 1 with arbitrary delta real number. Let me make a remark on terminology. Originally, in the papers of Luchko 1 and 2, this function with parameter delta 1 is referred to as multivariate Mittag-Leffler function. Later, in paper 5, the term multinomial Mittag-Leffler function is suggested due to the close relation of the coefficients in the equation 1 and the multinomial expansion 2. Since in the literature there exist many different definitions for multivariate or multi-index generalizations of the classical Mittag-Leffler function, we adopt the more specific term multinomial. In fact, we are mainly concerned with the following function of single variable t, given here, where all variables are functions of this variable t. That's why we find the term multinomial more appropriate and more specific, but Nevertheless, in the literature, both terms are still used. And this is no problem if the definition is given. Outline of my talk. First, I will start with the classical Mittag-Leffler functions. Then I will give some properties of the functions defined by Luchko. Then the Prabhakar type generalizations for arbitrary real delta, some basic properties, asymptotic behavior, and their complete monotonicity. As applications, I will consider an anomalous diffusion problem and representations of the moments of the fundamental solution, a linear viscoelasticity model with Mittag-Leffler type memory, and an example from physical chemistry, a model for diffusion controlled adsorption. Here I give the notations for the two derivatives that we'll use in this talk, the Riemann-Liouville and Caputo fractional derivatives, and the simplest form of fractional relaxation oscillation equation with the Caputo derivative of order alpha between 0 and 2, which solution is well known, given represented by the classical Mittag-Leffler function. Here for the some visualization, I give the behavior of this function for some values of alpha for negative argument, alpha between 0 and 1 that describe slow relaxation, and then alpha between 1 and 2, these damped oscillations are plotted on this figure. And first attempt for generalization when we consider a two-term fractional relaxation equation, and here we give the plots of the solution compared to the plots of the corresponding one-term equations, and see that for small times the largest order is determining the behavior, and for large times the smallest order, and this is behavior observed in later works. Further, the the classical two-parameter Mittag-Leffler function, its definition, and its asymptotic expansion for negative argument, which is very useful in applications, which implies this estimate 3, which is given in the book of Podlubny, and some classical complete monotonicity results concerning the classical Mittag-Leffler functions. Here the definition of a completely monotone function is recalled, and the simplest example of a completely monotone function, the exponential function of negative argument, and a classical result of Pollard from 1948 that Mittag-Leffler function of negative argument is completely monotone if and only if the parameter alpha is between 0 and 1, and after that sufficient and necessary condition for complete monotonicity for the two-parameter Mittag-Leffler function. This is, we continue with the function defined by Luchko. We consider only real parameters when mu are greater than 0, and not the most general case of parameters. We will use this notation for the multinomial Mittag-Leffler type function. This is the function which emerges in applications and give its Laplace transform, which is useful. So this is the function, and since it emerges in the solutions of multi-order fractional equations, let me give an example. The multi-term fractional relaxation equation in two terms, equation 5 with Caputo fractional derivatives, and equation 6 with linear combination of Riemann-Liouville fractional derivatives. The combinations are with positive coefficients, and the orders of fractional derivatives are between 0 and 1. And here we give the representations of the solution in case of problem 5, representations of the two functions u and v. After that, for problem 6, all of them are represented in terms of multinomial Mittag-Leffler functions. And let me note that all functions u and v in both cases are completely monotone. And in this way, this property known from the single term case is generalized. It's is true. The multinomial Mittag-Leffler function plays a crucial role in the study of multi-term time fractional diffusion equations also. Consider some papers that consider this type of equations are given in here. The time-dependent components in the eigenfunction expansions of solutions to initial boundary value problems for such equations are expressed in terms of these functions. That's why estimates for the multinomial Mittag-Leffler functions that generalize estimate 3 are essential in the study of such problems. And for the first time, such an estimate is given in the paper of Yamamoto and co-authors 7, which this estimate is obtained for parameters beta between 0 and 2 and mu between 0 and 1. And it is supposed that for the first argument, for the first variable that corresponds to the largest mu1, it can belong to a sector of the complex plane that contains the negative real axis. And for the rest of the variables, it's supposed that they're negative and bounded. And this estimate is obtained. It's very useful, and it is later generalized for the functions with less restrictions on the parameters. In these works are given some generalizations. Let me note that I learned about the papers 11 and 12 during the talk last year at this seminar series of the second author, Karel van Bokstal. So it's indeed a useful series of seminars. This generalizations is given in paper 12, generalization, where beta can be arbitrary positive number and mu are between 0 and 2. Assumptions on the variables are the same as in the theorem of Yamamoto, and the estimate is the same. An open problem here can be stated if the assumptions on the variables can be relaxed and to, if it's possible, to find some estimates for if one of the variables is possible. This is interesting because such models are given in the paper 13. And in the paper of Yamamoto, some remarks concerning these problems are given. We continue with generalizations of Prabhakar type, the classical Prabhakar function, and corresponding complete monotonicity results when alpha is between 0 and 1, and these inequalities are satisfied. Then this function of Prabhakar type is completely monotone. We will generalize this result. And the asymptotic behavior of this function, both the results are useful in applications, and they can be found in the review paper 14. We want to generalize these results for our function. And this is the multinomial generalization of Prabhakar type, where in general Zj are complex numbers, all parameters are real, and mu j are positive. I recall that this function naturally emerges in the study of initial boundary value problems for multi-term time fractional equations with non-local boundary conditions, and I will explain shortly here why. When the boundary conditions are non-local, then the eigenspaces could be multidimensional. In the our case considered in paper 4, they are two-dimensional, and this is the form of the eigenfunction expansion. And the first time-dependent component is can be represented in terms of multinomial Mittag-Leffler functions of Luchko, but the second term contains convolutions of such functions, so that it was necessary to define these such functions. And they have the following form. We use this notation for a short notation for the multinomial Mittag-Leffler type function of Prabhakar type. These functions form a class which is closed under convolution. And these basic relations are valid for this function. Combining first two of them, we can give a relation for fractional order differentiation of this function, and the third relation is give the representation of convolution of two functions of this type. These three relations, they generalize similar analogous relations for the classical Prabhakar function. And the Laplace transform is given by this relation. After that, the complete monotonicity result, which is also a generalization of the complete monotonicity result for the Prabhakar function, if all mu are between 0 and 1, and mu1 is the largest of them, and it satisfies these inequalities, Ag are greater than 0, then the multinomial Prabhakar function is completely monotone. these are sufficient conditions, but let me know that the assumption beta less or equal to 1 is also necessary for complete monotonicity, and we can see this from the asymptotic expansion for small times given here, which follows directly from the series expansion of the function. And here I give also the asymptotic expansion of the function for large times. And these results and the proofs can be found in paper 15. The complete monotonicity result is proven based on the theory on Bernstein functions and related classes, special classes of functions. This technique is simple and very useful when we would like to prove complete monotonicity or other similar properties. The use of this theory, of this technique, is motivated for me from the works of Gorenflo and Mainardi. So I would like to represent shortly the solution. Here I give the simple definitions of Bernstein functions, Stieltjes functions, and complete Bernstein functions. All these sets are convex cones. Every complete Bernstein functions is a Bernstein functions. Any Stieltjes functions is completely monotone. And two basic examples of Stieltjes functions and complete Bernstein functions. So, and a selection of some properties which we can use in the proof of complete monotonicity of our function. The definitions and proofs of these properties can be found in the book 16, chapters 6 and 7, and in property 3 is from the book of Grippenberg and co-authors. So for the proof of complete monotonicity of our function, we use property 3, the criterion given in property 3. So it's sufficient to prove that the Laplace transform is a Stieltjes function and this limiting property. Under the first, we prove a proposition under the assumptions on the parameters. These two functions are complete Bernstein functions, which follow from property P8 on the previous page. And plugging in it these complete Bernstein functions. So using this proposition, we can prove the complete monotonicity result concerning our function. Here I formulate it again. So we apply criterion 3 and we have to establish this that the Laplace transform is a Stieltjes function, which is equivalent to proof that function f is complete Bernstein function. We consider two cases, and in the first case we represent it as a product of two functions which are complete Bernstein functions, and this representation allows to use property 7, which implies it's complete, that this is a complete Bernstein function. And in case 2, this is even easier. And we use that the composition of 2 complete Bernstein functions is again a complete Bernstein function. So it is proven that the Laplace transform is a Stieltjes function, and this limiting property follows directly from the Laplace transform of the function. This is the proof, and it is an example how we use the simple Bernstein functions technique to prove in a simple way using elementary operations of functions of those classes to obtain new functions from the same classes. What is important, we can consider a pair of Sonin kernels here in terms of multinomial Mittag-Leffler functions. And since one is completely monotone, if and only if the other is completely monotone, we can formulate the corollary from our complete monotonicity theorem, which is stated here. Under the same assumptions on the parameters, we obtain complete monotonicity also for the Sonin, the other Sonin kernel. This is an important result because we can use completely monotone multinomial Mittag-Leffler kernels to define general fractional calculus operators in the sense of Kochubey. The definitions are given in this seminal work 18. And for these definitions, it is important, it is essential that the kernels are completely monotone. And now some applications. As a first application, we consider diffusion equations in 2 forms. On the real line, one-dimensional diffusion equations. The first one with a linear combination of Caputo derivatives, and the second one with Riemann-Liouville derivatives. To define the fundamental solution, we assume these initial and boundary conditions with the Dirac delta function. Explicit solution of these equations cannot be given, but we can give explicit representations of the moments of order gamma from this for these fundamental solutions, which are given here in terms of multinomial Mittag-Leffler functions. If gamma is 2, then we obtained the mean square displacement. And from the properties of multinomial Mittag-Leffler functions, we can obtain, derive properties of these moments. And we can say that for example, the asymptotic expansions, which is derived from the already obtained results for the multinomial Mittag-Leffler functions, are in agreement with the results in the paper 19, for example. The next example is from linear viscoelasticity. Consider wave propagation in viscoelastic half space, which is given in with these equations. Here, the function u is displacement, and the function m is a given memory function. Let us take for the function M a binomial Mittag-Leffler function with such restrictions on the parameters. These restrictions imply that this function is completely monotone and the integral of it is less than 1. And after that, we can represent the relaxation modulus. It is obtained also in terms of multinomial Mittag-Leffler function, of a binomial Mittag-Leffler function. The relaxation modulus is characteristic of a viscoelastic model, is a characteristic function, so it's an important function. Its properties are important and can be derived from the properties of already obtained from this for this function. From the representation of its Laplace transform, we we can say that this viscoelastic model provides a generalization of both the multi-term fractional Zener model and the Havrilak-Negami relaxation model, which are considered in papers 21 to 23. And this model with binomial Mittag-Leffler functions is studied in paper 20. And a last example, maybe not so popular, it's from physical chemistry. Let us consider first a classical problem of diffusion-controlled adsorption of surfactants. Here we have a fluid and molecules of some surfactant. For example, this can be water and molecules of soap. And an interface where usually a surfactant, it likes to go to the interface. So the concentration of surfactant in the fluid is denoted by C, and we are interested in the evolution of concentration of surfactant on the interface, denoted by G of T. It is a classical situation. First, we have a diffusion equation in the bulk phase and some initial and boundary conditions. And the evolution of the concentration G is given by this relation, where CS is the subsurface concentration given by the relation here, where F is a given function, usually nonlinear. So this is a typical classical problem with integer order equations. But when we solve it, we arrived to the following fractional order equation of order 1/2. This is a classical equation called Vartorde equation. It's from 1946, but this is a good example how from classical integer order problems we can obtain fractional equations. And generalization. Here we have two phases and an interface with similar equations in both phases. This is adsorption-desorption process when we're supposed to have anomalous diffusion in both phases. So here we have all equations, given also here equations, time fractional equations for Animal's diffusion, and initial and boundary conditions in both phases. And here the concentration of surfactant on the interface, its evolution is given by this equation, which leads to an ordinary differential equation for the function g, given here, which is multi-term equation with fractional derivatives of different orders. This equation is usually nonlinear, but we have this relation. And if we suppose that function f is linear, then the equation for g is of this multi-term form, a linear equation, and we can obtain its explicit form of its solution, given as a sum of multinomial Mittag-Leffler functions. This representation allows for analytical study of the solution based on the properties of the binomial Mittag-Leffler functions. And this is a work in preparation. So this was the last example. And as a conclusion, we see that the attention of mathematicians and applied scientists towards the functions of Mittag-Leffler type is increasing because of their relation to fractional calculus and its applications. And in particular, the multinomial Mittag-Leffler type functions emerge in various applied problems. Therefore, the knowledge of their properties is useful tool in the study of such problems. For example, for assessing physical acceptability of the models, for establishing well-posedness and regularity of solutions, the asymptotic behavior, complete monotonicity, etc. This all motivates further research on the multinomial Mittag-Leffler functions, expanding the range of considered parameters and the studied properties. And let me say also that it is an increasing number in the last years of generalizations of the classical Mittag-Leffler functions, different from the functions considered in this talk. And for recent surveys on different generalizations and other special functions of fractional calculus, we can refer to recent review papers by Virginia Kyriakova and other authors, and also to some future talks in this seminar. So thank you for your attention.
Thank you very much for the nice talk. Do we have any questions or comments? I had actually one comment and one question. Could you go please to the very first page? Yes. So this comment probably you were already aware of, but I just mention it for the other people listening who might be interested in these functions. So with the original so-called multivariate Mittag-Leffler function with delta equals 1, the two papers that you have mentioned on this slide, Luchko, Gorenflo, and Luchko, they are perhaps the most cited papers about this. But the first place where this function was defined was actually in a paper of Gorenflo and Luchko that first appeared in 1995. So before these two papers as a preprint, although I think it was published in a journal only in 97, but that was about the Abel integral equation with this operational calculus method. So that was the very first time this was defined. Also, paper number 3, just that's only the bivariate. So it's basically the case m equals 2 of your function. So it's like a particular case, but yeah,
but
thank you for mentioning it anyway.
the idea is the same.
Yeah. I also have a question, maybe trivial question. You've talked a lot about the property of complete monotonicity. Could you give an intuitive explanation of why this is important?
For example, maybe in the second example, in viscoelasticity, usually this relaxation modulus is considered completely monotone. It is good when it's completely monotone. This is maybe one example here when it is it's good to have complete monotonicity. Also, maybe it helps in some way to prove the positivity of solutions for two diffusion equations. But it's not straightforward to it's an interesting question. Yeah, it's good to think about it.
Okay, thank you. Pavan, you have raised your hand. You have a question?
I don't really have a question, but the application part was more of interesting to me, especially the last one of the last one. So probably you might be aware or probably not aware. So I just wanted to share with you that last year we also looked into turbulence modeling for using fractional and non-local operators. So that could be a useful thing to use. So I just wanted to mention this.
Yeah, thank you. This is important. This is mainly the subject of work of my co-author, but it's good to know. Thank you.
Thank you. Katarzyna Górska?
Yes, I would like to comment that this completely monotonicity. I'm physicist, and why we need it. When we describe the diffusion, we want to show that the solution is positive, non-negative, and because it's a probability density function. And we are using the Bernstein theorem, such that we know that according to this theorem, there exists the relation between the completely monotone functions and non-negative functions. And this is one reason. And in a relaxation, there is relaxation functions. And they are also defined from 0 to 1. So it is only also positive functions. And this is the reason why we need the completely monotone function. So I know these two reasons for that. But Emilia, I would like to say that really it was a pleasure to hear you.
Thank you very much. And thank you for the explanation of the physical side of these properties. The importance of this.
For us, we are looking like that. I look like that. Okay, thank you.
Thank you very much.
Can I ask a question, please?
Yes, Ravshan Asharov, go ahead.
Yeah. First of all, thank you very much, Ms. Dekova, for a very interesting talk. Can I see this page 9, please? This is just simple question. Page 9.
Yeah.
Yeah. Here at the end, you say that this Mittag-Leffler function is completely monotone if and only if alpha is less than 1. But if alpha is 1, then this is just exponential, and it is here it is written that it is a completely monotone function.
Yeah.
So it is not if and only if.
Indeed, it's maybe this is a misprint. It
Yeah,
be
sorry.
less than or equal to 1.
Yeah, thank you very much.
Thank you.
Thank you.
So I'm sorry, I cannot activate raising hand, but may I ask a question, please?
Yes, of course.
Yes. So, Emilia, thank you very much for your very nice, interesting presentation. And of course, the results are very important and very interesting. So, in your talk, you focused on analytical properties of the multivariate Mittag-Leffler function. But what about numerical calculations? I mean, even in the case of the classical Mittag-Leffler function, it's not so easy to develop numerical methods and routines for its numerical calculations. What about bilateral and multilateral Mittag-Leffler functions? Are you aware of any results regarding numerical calculations or algorithms for numerical calculation of this function?
Thank you for the question. No, we didn't study numerically these functions, and I did not did research on that. But it's indeed important to be able to numerically calculate them. Yeah.
For practical applications, especially, I mean, for plotting some solutions and for all these things, yeah, would be very interesting. Maybe you should involve Roberta Garappa, who is a specialist in numerical calculations, especially for Mittag-Leffler function.
Yeah.
Maybe Marina Popolozzo can also participate in this study because she is also involved in these activities regarding numerical algorithms for calculation of special functions. Would be very important, I think, yeah.
Thank you for the remarks.
Thank you, Yuri and Marina. Thank you for citing me. Can you hear me?
Did you probably already started to do this multidimensional
No, actually, we haven't.
Mittag-Leffler and right functions? No, not yet, yeah?
No, we haven't considered this problem. We have just worked with the Prabhakar function, but no more than these parameters. Maybe it could be interesting to work on this topic and find some numerical methods, because already the case with the 2 parameters is not easy at all. So it will deserve certainly some good methods.
Yeah, I guess that in the case of multivariate functions like Mittag-Leffler multivariate function, you will get you will need to involve some completely different approaches compared to the one-dimensional case. Would be a very difficult problem, probably.
Yes.
I actually have some ongoing work that's sort of relevant. I don't work in numerics, but I've been working on asymptotics of the bivariate Mittag-Leffler functions in the case m equals 2. So it's also motivated by applications, in fact, but it's been ongoing for several years and we have not finished this project yet. But even the bivariate case, as you say, with m equals 2 is very challenging compared with the classical Mittag-Leffler function. So maybe that would be one to focus on first for the numerical analysis before going to the general multivariate multinomial case.
Yeah, sure. Yeah. Probably you also have seen that even asymptotical behavior of the multivariate functions like Mittag-Leffler function is extremely an extremely complicated problem compared to the case of the one-dimensional case.
Yeah.
But still, these multivariate functions are very important, and they really appear in several applications. So we should continue to work with them and investigate analytical properties that can be considered probably more or less not in a very easy way, but still somehow manageable. And as to the numerical methods, I also thought about this problem some years ago, but I could not find any approaches to do this. So difficult problem.
Yes, yes. Thank you, Yuri, for the comments. Any other questions, remarks? If not, then let us thank our speaker again. Thank you for the nice presentation, for taking time to share this with us. And I guess I can stop the recording here.